you so much. First, thanks to the organizers for having me give this presentation. I've been working quite a while now in the JWST project as part of the NASA project science team. Also, this is the first time I've ever been in a very small workshop with scientists with another Stefanie that spells her name right. Okay, so we've been studying the solar system since cycle 1. There was a number of programs, including Guaranteed Time, that was dedicated to ensuring that we could actually observe objects a little bit closer to home. And what you're seeing is my own little montage, not to scale, of what we've actually imaged in the solar system. Not all objects are included. A lot of the small bodies are mostly point sources, but you can see that we've covered all of the giant planets, Mars, and a number of satellites with pretty good resolution. So that's quite exciting. So just to bring you all back to where we are, we're looking at endoplanet, not exoplanet. For the high redshift folks, this is Z equals 0. For the chemists, this is the Z non. We are definitely a little bit closer to home. And what are we trying to do? We're trying to understand the cosmic inheritance of volatiles. And JWST is really enabling this sort of study from a level that we've already been seeing in talks that have been presented over the last few days of protostars, disks, all kinds of star formation, and how that chemistry is actually evolving, how ubiquitous it is, and what that has implications for as far as for planetary systems, including the delivery of volatiles to terrestrial bodies. So we can think about this as far as the disk phase goes, and Inga actually brought up some excellent points about how much processing is actually happening during this phase, and really trying to understand what that process looks like so that we can get a better understanding of what the pristine nature is of either small bodies in the solar system, atmospheres in our giant planets, and what's actually being preserved. And this gives us a sense of, are there other planetary systems that could have been preserved from the same materials that made planets such as our own? So here is the collection of everything that happened sort of in cycle 1. These are all the targets that we had planned and have now been completed. The Kuiper belt list is certainly not inclusive, but you can see all your favorite ones included there, such as Pluto, Haumea, Eris. And everything from Mars on outward, a number of asteroids, near-Earth asteroids, Jupiter system, comets, a number of comets now, the Saturnian system, and the ice giant. So Geronimo Villanueva and I did an inspection of what we could actually do with planetary science, and this is using the planetary spectrum generator out of NASA Goddard. And we ran a number of simulations, just really exploring what chemistry we could actually understand about bodies within the solar system, everything from doing ortho-para ratios in water, understanding compositional studies up to complex organics, really disentangling volatile isotope ratios, especially for carbon monoxide, carbon dioxide, as well as studying the ices. So how much crystalline and amorphous ice is embedded within solar system bodies. And then, of course, the solid component, understanding the silicate nature, how much carbonaceous material or otherwise is within our solar system. So we'll start with Galileo, just because we're here. Understanding where we are as far as a planetary system and understanding that Earth is not the center of the universe, though I have some people that I know that think that they are the center of the universe. We'll let them think what they want. It's been clearly demonstrated that that's not the case. And we've moved on to this fantastic world of doing planetary science starting hundreds of years ago. So Galileo first looked at the Jupiter system. This is an amateur image of the Jupiter system and some of the major Galilean satellites taken with a telescope that would have been comparable to what he would have used. And you can see even still, you can start seeing band structure across the atmosphere of Jupiter, as well as the fantastic Galilean satellite. So following in the success, JWST, of course, started with Jupiter. During commissioning, one of my jobs was to make sure we could actually observe objects in the solar system, and that meant tracking targets that move with respect to the background stars, but also studying things that are extremely bright, such as Jupiter. Understanding what kind of persistence is happening within the detectors was a component of this work, but also what kind of contrast that we could actually achieve with simple observations. I will let you know that each one of these frames is seconds long, and we were able to do absolutely amazing data, including even in commissioning data with just a glimpse, already detecting the rings of Jupiter. So I got a gold star. We can detect and track moving targets. And of course, then the science actually started to begin. And one of the first systems that was observed for planetary science was the Jupiter system with the early release science team. And of course, the science data is actually much higher quality than what we were able to do during commissioning, because we weren't supposed to science any commissioning data. But they did a fantastic job, and this was also in collaboration with Judy Schmidt, as Janice was talking about earlier. So you can see not only the fantastic resolution across the disk of the planet, you see the great red/white spot in JWST data, the fantastic contrast that we're able to achieve by being able to detect the rings, which is a factor of 10,000 less bright than the disk of Jupiter. Small satellites that are tens of kilometers in diameter, and of course, aurora and other fantastic features. So this was actually part of the early release science team. We got one solar system object in early release science, and it was the Jupiter system, which was about 43 hours total. This team is doing amazing work, and they're even tracking satellites as well in the Jupiter system. So I have Galileo there with the JWST now. And you can see the fantastic types of achievement that they've done with data reduction, being able to not only pull out their rings, but track these satellites in moving frames. This was an extensive amount of work, and it is results that they are working on getting published. And of course, obviously the other Jovian satellites. I'll talk about Europa in a minute, but I did want to highlight that amazing work's being done in Ganymede, Io. We're looking at volcanoes. Of course, this isn't nearly as spectacular as what we've been seeing with the Juno images, but I promise you we're doing all kinds of spectroscopy and chemistry that Juno hasn't been able to achieve. So it's really quite complementary to what planetary missions are doing. And JWST is giving us fundamental spectroscopy and information about not only the surface distribution of these volatiles, atmospheric components, but also what the composition is. And I'll give you some fun new results for that in a second. So here's our montage of our giant planets. You've seen other versions of Uranus now, but when I made this, this was the one that we had at the time. Absolutely beautiful. And the one thing you will note is JWST is the ring machine. It's fantastic. We can see rings in ways that we haven't been able to see since the Voyager flybys. Keck can do some of this, but not all of it. And with JWST's resolution and spectral coverage, we're really achieving things that we haven't been able to do. I am not going to highlight much on the giant planets. Obviously, Henrik is speaking after me, and he will give you all the insights that you want to know about ice giants, or you can ask him in questions later, because he's told me he's not talking about a lot of it, because there's a lot. I will say, even with the fantastic images that have been released as science images that Klaus so cleverly designed for us, we are still sciencing them. And this was the first time we've, for example, been able to detect the Zeta ring. and getting all kinds of fun data out of these, even just images that were acquired just to be beautiful. We did have a program on Saturn and the Guaranteed Time program. We did a little bit of spectroscopy with MIRI, and then we also had some of the field set across the rings. We did NIRSpec and MIRI IFU spectroscopy. What you're seeing in the top right is some of the NIRSpec IFU of the rings. Lots of crystalline water ice features, Fresnel peaks, confirmation of deuterated water, the OH band with a 2% dip that was found by the Cassini mission. There's confirmation again that there's no carbon dioxide, but we are seeing a little bit of hint of possibly some hydrocarbons in the near-infrared spectra. With MIRI, we did a couple of filters across the rings, and we were able to get a number of rings in one sort of setting. You can see that depending on wavelength, the rings really light up or they really disappear. And this is mostly due to the composition, but also the angle of the rings at the time. So here's the mid-infrared spectra. The shaded regions are actually from Saturn, but you can see how a background black body was actually fit to these data to acquire, and confirmation that we are dominated by primarily crystalline water ice. And again, the whole composition is confirming a lot of what we found with Cassini, but with even better data and better signal to noise. This paper was just accepted in JGR. Mars. Mars is the brightest thing JWST will ever look at. It is the brightest thing in the infrared sky at the James Webb Space Telescope wavelengths, and that also gives us a lot of limitations. The best part about when I started on the project was they said, you will never be able to observe Mars. Exhibit A. Here's Mars for you. We did imaging and spectroscopy. You do have to use a very specific set of filters. We kind of took advantage of hiding in windows where Mars wasn't quite as bright, and we were able to do a number of different things. Including confirming, or if you are a Mars scientist, saying that they discovered water on Mars. Again. We do have beautiful water spectra. We're digging deep into the organic section of this and really trying to push on the methane abundance. And that's something that the team is working on very diligently. These were some of the first data that were acquired, and they were, obviously calibration issues were challenging. But also when you're considering how bright Mars is, we had a number of challenges. So this data has been quite complex. Now I'm going to take you to the outer solar system. JWST has now accomplished observing the most distant comet ever. We have never observed a comet at 46 AU, and we were able to actually observe Hale-Bopp. This is a fantastic project that was a GEO project. That was complementary actually to some Hubble data that was being acquired, trying to measure the nucleus size of Hale-Bopp. Comparisons are being made about it's not flat spectrum, and we're getting a lot of unique insights about what this composition is. It's probably due to organics, maybe potentially organic salts that was found in 67P. But at this distance, we think that we're actually attributing this feature more on water ice absorption at the 3 micron region. But more modeling is going into this, and they're actually doing some grain studies as well to really pin down what this abundance is and composition. Speaking of the outer solar system, trans-Neptunian objects are sort of the bread and butter for JWST in the solar system. We haven't had a lot of access to really understand the composition of these objects in extreme amounts of details. In cycle 1, there was one large program awarded to the solar system group, and that was to do a survey of trans-Neptunian objects. This survey included 59 objects, and then complemented with what guaranteed time observations. There's over 100 that have been observed in the first year. What's been amazing about these observations is the spectral wavelength that we've actually been able to achieve and actually been able to measure towards some of these objects has revealed that we are getting sort of a compositional family variation in the outer solar system. So the lead author, Noemi Pinella Alonso, and her group has now a couple of papers that are accepted and in work, basically describing now this new classification of trans-Neptunian objects. And they call them the bowl, the cliff, and the double dip. This is based on statistics of what these spectra look like as far as the water absorption and carbon dioxide absorption features. Really exciting stuff. But more fun is new work that's actually just been released on some of the large trans-Neptunian objects, Makemake and Eris. These papers actually just came out about a week ago, maybe 2 weeks now. And we have fantastic spectral data on these two large objects. So, oops. Okay. So here is the near-infrared spectrum of Eris. You can see it's absolutely fantastic with all types of methane features. The ones that are labeled are the 3 nu 4, nu 3. Those are the new methane bands that have not been observed before towards this object. But most importantly are the striking features of deuterated methane. Deuterated methane was actually so prominent in both of these objects that D/H ratios could actually be measured. A lot of work went into the analysis of these data, a lot with the calibration again, and really trying to understand what contaminants there might be, so nitrogen ice, for example, and pulling out these things with rather detailed models. So through this, we found that there were D/H ratios, I'm sorry, that's so small, of about 2 × 10⁻⁴ in both of these objects. But the carbon 12 and 13 still look solar, or terrestrial, sorry. So this was an interesting result. Seeing the deuterium over hydrogen ratios led to a lot of speculation about what could be causing a deuterium fraction that looks something like water in comet. We have one measurement of deuterated methane in a comet, and that's from the 67P results in Rosetta. And it was actually on the order of 2 × 10⁻�3. Recently, well, not recently, I'm sorry, Ilse Cleaves actually published some models suggesting what fractionation could be in the outer solar system, sort of beyond 20 AU, kind of overlapping in the Kuiper Belt region, giving us results that were very similar to what was found with 67P. So that primordial sort of D/H ratio is inconsistent now with what we've measured in trans-Neptunian objects. So extensive models went into place, trying to understand how we could get fractionation and how methane, deuterated methane specifically, could be found within these objects. And a fantastic set of papers just were published, one on achieving the D/H ratio, but the other one on doing some geothermal models. And in this paper by Glein, they really tried to understand what the primordial contribution could be for methane on these icy worlds, whether or not there was abiotic or thermogenic processing that could actually cause a deuterium fraction that we've measured. And basically, they were able to rule out the primordial. As I just said, we had an abundance that's an order of magnitude lower than what they would have suggested for a primordial abundance. And it's probably some combination of abiotic and thermogenic processing, basically with the conversion of carbon monoxide, carbon dioxide, and subsurface, blooming more methane out. But of course, the best thing in the solar system are comets, because that's what I do. So I had a guaranteed time project to study a target of opportunity comet in cycle 1. We were able to keep our eyes on the sky, and with the assistance of amateur astronomers, a new comet was discovered, and we were monitoring it rather closely and found that comet E3 from the Zwicky Transit Facility, which it was named for, was an ideal candidate for us to do for James Webb Space Telescope. We got fantastic data, near spec all the way through MIRI, and this is, I promise you, the best comet spectra you will ever see. Also, again, because it's mine. So what you're seeing is the actual high resolution data in black and our model fit in red. And it is almost completely perfect, but I'll give you a little bit more, and yeah, you can really see the fun in all of this. So just highlighting some of my favorite things, we do have carbon isotope ratios in these data. The comet was bright enough though that everything is saturated, even the hot band. So we are digging into this data and doing full modeling across the entire IFU spectra, just so that we understand both the temperature profile of these species across the coma and really getting a full abundance ratio. And we'll probably make abundance maps based on these data, since we do have maps. The organic section of the spectra in the near-infrared region is very intriguing. We see all of our standard candidates. I'm sorry you can't see all of the list of organics there. I promise you they're all the ones that you already know and love in cometary organics. And what you're seeing on the right is sort of that 3 micron region where a lot of the more complex organics start stacking up. And what you're seeing is the data in blue and then our best model fit in orange. And the bottom panel right below it is actually the residual of this fit. This is absolutely due to the lack of data that we have in this region for gas phase methanol. We believe it's methanol, methane/methanol. And we're working on getting some more laboratory work conducted so that we can actually fit these data and really understand what's underlying in this organics region. Most importantly, not only do we have beautiful spectra, but we can now put these spectra into cometary maps the way that we've been doing with the ALMA for the last decade. And we're able to map volatiles that we don't have access to from the ground to mid-infrared, as well as carbon dioxide now, which we haven't had access to. So we're now getting, real structure, 3-dimensional structures of comet coma, understanding the dynamics of how the outgassing is occurring and how that's influencing the chemistry that we're able to observe remotely and see how that's relative to the native component of the comet nucleus. How pristine is that nucleus, and is the chemistry that we're observing remotely indicative of a primordial abundance? This is really cool because this was something we were only able to do with flyby missions. So this is the Hartley 2 data in the upper right, showing you that we were able to map this in a flyby approach. Now with JWST, we don't have to fly by comets. We can just simply point and shoot, and we get mapped. This is just a little montage of all the comet projects that I've been involved in. So we have everything from periodic comets to new dynamic objects to more distant objects. And you can see that there is quite a diversity in the spectrum. We only have 1 comet of the 4 that are shown here that has a lot of carbon monoxide. The others really don't have hardly any at all. So this is really fun data that we're digging into. And one of my favorite projects that we're working on, I keep hitting the wrong button, is we're trying to see whether or not the polycyclic aromatic hydrocarbon features are actually embedded within these data. PAWs have been something that have been a challenge for comets for a very long time. IDPs definitely have signatures of aliphatic and aromatic carbon, and we've seen with Rosetta, there are small PAHs that have been found and detected with the Rosina instrument. So really trying to understand what this looks like with remote sensing is a real challenge, and it's really taking a lot of modeling to understand what's going on. So we've been working extensively. This is primarily work that's been done by Diane Wooden at NASA Ames, where we've been really digging into the especially 3 to about 10 micron region and trying to dig out any PAH features in the noise. We definitely are seeing evidence of some things. Most important to note, we do not see the 3.28 PAW feature, but we are seeing some emission that's the 3.42 micron feature, and then a little bit of evidence of the 6.3, 6.9, and 7.2. This is absolutely very preliminary data. We're still working on, again, we have to get this region in the 3 micron region. We need some more simple volatile organic spectroscopy to be done to really disentangle what the significance of that feature is. But I think this is going to be a really exciting result and possibly a way forward for detecting PAHs throughout the solar system. Speaking of more solar system objects and small bodies, we've also been observing things a little bit closer to home. So we had a fun project that was basically, it occurred because of the launch delay. As you all may know, the guaranteed time programs were established a number of years before launch, and unfortunately, comets and asteroids come and go every year. And whenever we had our final new launch date and had to redefine our programs or confirm our programs, I had to provide another list of comets for our guaranteed time program. And so the person that I had in charge of periodic comets is a colleague, Mike Kelly, at the University of Maryland, and he came to me and he said, I have a crazy idea. And I was like, well, that's what we want to do with guaranteed time. We want to do the crazy stuff. And he's like, okay, there's these objects that reside in the main belt, the main asteroid belt, that are fuzzy. They look like comets. We've looked at them with every observatory on the ground and in space prior to JWST and cannot determine what is driving activity of these fuzzy dots that reside in the asteroid belt. And so we took a look with JWST towards this main belt comet called 238P. And here's the NIRCam image, just so I can show you that it is a fuzzy dot. It does indeed look like a comet. And here's the spectrum. So compared to Hartley 2, which is a very familiar periodic comet, which is the upper 2 spectrum of the upper panel, the 238P Reed spectrum is the one on the bottom in black. And what we can see is a very notable water emission feature. This is the first time water emission's been detected in a main belt comet towards one of these active bodies in the asteroid belt. This was a huge result. This means water is in the asteroid belt. There's no carbon dioxide, which is also an interesting finding because we see carbon dioxide in every comet we look at. So what's the origin of this water? How did it get there? How is it being preserved in the main asteroid belt? We do not believe that this is a captured Jupiter family comet because of the inclination of the orbit of this object. So this is really a nice, interesting finding and gives us a lot of promise for having more volatile material being preserved in bodies like asteroids in our inner solar system. There's the numbers if you want to know. Speaking of water, we have a lot of water throughout our solar system, and we have these fantastic bodies that we call ocean worlds. If JWST is going to be finding habitable environments or biotic signatures or prebiotic chemistry, I think the solar system is going to be the first place that we find it. I love the exoplanet work, but I think the odds are in our favor. We actually have ocean worlds. So the Hubble Space Telescope started by observing these plumes of gas that were coming out of Europa, and the spectroscopy suggested that there was definitely water that was being expelled from this particular moon. We also saw some variation across the surface of Europa with Hubble, again, showing that there's some sort of reprocessing occurring on the surface. So with JWST, we had big ambitions, even before launch, of what we were going to do with this ocean world. The IFU fits beautifully across the disk of Europa, where not only could we take one of our little spaxels and put it across the plume, but we could also sort of map across the disk and infer what's going on with these plumes of Europa. And so this is our data. So this is the NIRCam data as well as the NIRSpec data. And we did not detect a plume, but we did actually detect carbon dioxide ice across the surface. Again, taking advantage of these spaxels, we can see beautiful carbon dioxide ice and water ice across the disk, having significant implications for a source of carbon that's actually coming to the Europa surface from the subsurface. We have no reason to believe that carbon dioxide would be coming from any other region. And so this is indicative of a carbon source that's internal to this particular moon. Other ocean worlds include your Enceladus, one of the moons of Saturn, excuse me. Enceladus is responsible for this beautiful E-ring, and with JWST, we took a nice snapshot of it, and we have a moon that, we have a plume of water vapor that was detected. It actually ran off the edge of the IFU, and the plume was so big, it's 20 times the size of the moon. And my fun fact for the Europa water, 79 gallons per second was actually measured of water vapor being spewed out of this moon. At this rate, you can fill an Olympic-sized swimming pool in just a couple of hours, in comparison with doing so with a garden hose on Earth, which would take more than 2 weeks. Okay. I'm gonna quickly go through Titan because this is brand new results. We just submitted this paper last week. Titan has been a fun ocean world. It's one of the most unique moons in our solar system. And this is the part where I get to look at the exoplanet folks and say, look at that. So here's near spec from Titan. Beautiful hydrocarbon emission. Not too many surprises until you get into the mid-infrared. Again, look at that. It's not flat. Isotope ratios, but more importantly, the detection of a new methyl radical. This is the first time this has been detected on Titan, and we were able to do so with JWST. I'm not going to go into any of those details in the interest of time. So JWST is really enabling and enhancing the science return of solar system observations. It's extremely complementary to other planetary missions, as well as what we've been able to do from the ground for the last 100 years, and even into the more recent past. We're really giving a lot of comparative planetology to exoplanets with the study of what we are doing, having the same sort of science coming out of the solar system bodies that we can compare now to exoplanets is really informing. And of course, coupled to disk, star formation, as well as exoplanets, we're really understanding the nature of pristine bodies in the solar system and how they're preserved and informing us about what processes are occurring. Thanks for your time.